Hi, my name is Jaden Watt, and I would like to present my final year project in the study of ammonia as fuel for an internal combustion engine. This project has been industry sponsored by ResTech. Okay, so in the effort to save us from the threat of climate, some of our most touted renewable energy solutions may be destroying the environment. We are, of course, making the necessary and ungraceful initial steps towards solving a complex problem. However, our good intentions may be doing more harm than good. I'm not going into all the negative features of current technology here, and I'm not proposing the perfect solution, nor does one exist. However, I do believe what I'm going to talk about could offer up a significant improvement towards implementing clean energy. Renewable intermittency usually requires a fossil fuel backup to supplement times of undersupply and can impact the stability of the grid in times of oversupply. As a result, we need storage, which means batteries. However, current lithium-ion battery technology used for energy storage and electric vehicles are expensive. They're also energy intensive to manufacture, and mining of its constituent metal comes at a high environmental and human cost. Furthermore, with a short life of around 10 years and low recycling rates of 3 to 5% globally and in Australia, it is expected that 11 million tonnes of lithium-ion batteries will reach the end of their service lives between now and 2030, leading to the generation of significant amount of toxic waste and subsequent ecological contamination, usually in poorer nations that accept our waste. So, what's the alternative? Well, another form of chemical energy storage, fuel. A carbon-free fuel, that is. If the energy used to synthesize the fuel comes from renewable sources, the entire cycle can be made completely carbon-free. More specifically, using wind or solar to power a plant to make 1 part nitrogen from air and 3 parts hydrogen from water in the Haber-Bosch process to make ammonia. A smelly, toxic gas, ammonia doesn't exactly scream clean energy future. But although it might not make you feel warm and fuzzy yet, allow me to point out why ammonia is starting to gain global interest. First of all, as mentioned, it's carbon-free. The ammonia generation would store the clean energy and then later be able to fuel gas turbines, fuel cells, or reciprocating engines without direct CO2 emissions in a process such as the one here. Additionally, ammonia is a hydrogen energy carrier. It is more volumetrically hydrogen dense than liquid hydrogen, but much easier and safer to store and transport, being liquid at room temperature and relatively low pressure, with well-established infrastructure already in place. Which is why the CSIRO have developed a method to crack the transport of ammonia into hydrogen for use, instead of storing hydrogen itself. David Harris from the CSIRO points out that ammonia is the key enabler for exporting renewables. Lastly, we can see here, ammonia is substantially more energy dense than lithium-ion batteries, but not as high as conventional fuels such as petrol or diesel, which we will revisit later in this presentation. The carbon-free and energy-dense nature of ammonia is the foundation of this project, whereby we are investigating the use of ammonia in an internal combustion engine for small-scale power generation, in the hope of providing off-the-grid power for rural homes. Although fuel cells may present the most efficient solution to using ammonia fuel, they are still expensive and would not be an affordable option for homeowners at this time. In this final year project, the overall objective is to compare and optimize performance characteristics of a spark ignition engine using ammonia as fuel compared to conventional fuels, including all design and safety considerations in implementing the ammonia system. In consideration of ammonia's limitations, I have a few listed here. So firstly, we have high auto ignition temperature. That's 2 to 3 times that of petrol or diesel. That is the temperature at which it auto combusts without spark, which makes it difficult to use in a diesel engine, requiring impractical high compression ratios. This is, however, alleviated by its high flammability limits, allowing for more fuel to air in the combustion chamber. We also have a high latent heat of vaporization. That is the energy required to phase change from a liquid to gas. We'll see that later. That's an important fact. And lastly, slow flame speed. It is 1/5 that of petrol. That is the velocity of the flame in the combustion chamber, which can result in engine knock or misfire. Misfire is a risk of releasing unburned ammonia known as ammonia slip, which is hazardous to human health at fairly low concentrations. Finally, imperfect ammonia combustion trades one problematic pollutant, carbon, for another, nitrogen. If you're not familiar, nitrogen oxides, or NOx, are responsible for ozone depletion, smog, and acid rain. It is the reason you have a catalytic converter on your car, but similarly, there are processing techniques to mitigate NOx on an ammonia engine to acceptable emissions. To alleviate these problems, a combustion promoter is usually required. The ideal promoter is hydrogen, given that it produces no carbon, has the highest reported thermal efficiency, and would not require any additional storage. As part of the ammonia could be cracked to account for 5 to 15% of the fuel mix. However, we did not have access to this technology or the ability to store and combust hydrogen safely. Therefore, the project considered the use of a hydrocarbon promoter. Given we are using a spark ignition engine, we investigated the use of petrol as a combustion promoter. The optimal mixture suggested in the literature is roughly 70% ammonia to 30% petrol. The use of petrol is justified by a dramatic reduction in carbon emissions at low petrol mixtures, 75% reduction at around the optimal fuel mix. The linear relationship is shown here. The literature shows that use of ammonia also demonstrates a significant improvement in the engine's efficiency and performance than just petrol alone. This study, for example, achieved 32% brake thermal efficiency at 68% ammonia mix. Dependent on performance characteristics such as compression ratio, equivalence ratio, timing, and inlet pressure and temperature. The engine used for experimentation in our project is a 16 horsepower rated stationary engine, initially carbureted, coupled to one of the eddy current dynos in the EC building test cell. After the design and fabrication of the exhaust incorporating a lambda oxygen sensor, we could perform baseline engine tests using petrol. The engine is controlled through the dyno controller and some installed software. The transient response is controlled through the software, though this settling time was difficult to decrease beyond a certain point. This is the operating interface while performing testing, which I think is very cool. The performance of the engine is shown in this service plot of power and torque as a function of RPM and speed. The torque peak is around 25 Newton meters at approximately 2,000 to 2,500 RPM. They are fairly unreliable at this stage with pretty significant fluctuations in the measurements. The engine is designed to operate at a wide open throttle that is around 3,600 RPM and beyond. As such, poor performance was observed in the low RPM range and even stalled below 1,500 RPM. The results also need to be repeated due to an error with the controller limiting speed beyond 3,500 RPM. Very high air-fuel ratios were also observed when the load of the dyno was applied, as you can see here. For context, the stoichiometric air-fuel ratio for petrol is 14.7, which is much lower than what we were achieving. Additionally, infrared video was taken of petrol operation. The maximum temperature observed was around 495 degrees Celsius. Temperature rises at higher loads due to higher mass flow rate. And it will be interesting to observe ammonia exhaust gas temperature with lower air-fuel ratio, and if the temperature range will be suitable for selective catalytic reduction to control NOx. So this will be compared in future. To test the petrol ammonia fuel mixture required a dual fuel system design. This requires converting the existing carburetor to electronic fuel injection. In this system, there are separate tanks for ammonia and petrol, simultaneously injected into the intake manifold, as shown in this piping instrumentation diagram, if you can see here. The intake manifold was designed to incorporate the petrol and ammonia injectors, allowing the injected fuel to be pushed through by the airflow through the butterfly on the throttle body. The manifold was designed in Creo and printed in Onyx high temperature nylon composite. It's this black part connected between the engine and throttle body shown here. There were several design questions around implementing this system. For example, should we inject liquid or gaseous ammonia? What flow rate is required? What size tank do we need? There is no, there is no commercially available injector for gaseous fuel. So an LPG injector was purchased on the intention of injecting liquid ammonia. The problem with injecting liquid ammonia is the previously mentioned latent heat of vaporization, consuming a large amount of energy and cooling the in-cylinder air temperature, which is further exacerbated by requiring more ammonia fuel to provide the same energy density as petrol. Furthermore, after consulting with BOC gas, the standard method of drawing ammonia from the cylinder is allowing part of it to vaporize in top of the cylinder and drawing the gas. Based on required flow rate calculations seen here, at the peak of around 80%, we would need approximately 92 grams per minute of ammonia. Ammonia is the blue line seen here. So the gaseous flow rate of the LPG injector was quickly tested. This was done with compressed air, first by inflating a balloon and measuring the displacement of water over time, and then more accurately using a bubble flow meter. Unfortunately, I applied too much current to the injector on this final test and burned it out. Due to the large difference in density from gas to liquid, liquid is much more volumetrically efficient and consequently requires a much lower flow rate. The test demonstrated that the gaseous flow rate was 1/20th the required flow rate for the engine. Therefore, we were back to liquid, although it is not standard practice to draw liquid. This requires maintaining pressure all the way to the injector. Initially, we suggested to simply turn the bottle upside down. However, this could not be recommended by the supplier. So we needed a dual port valve and an auxiliary cylinder of inert gas to drive the flow, as seen here. It works by the same principle as a juice box, and the inert gas works as a piston to force the liquid through the line. Given we are now injecting liquid, the air or fuel stream may be heated prior to the injection to counteract the vaporization cooling problem. An integral part of the viability of this project was safety. To be able to safely use ammonia in testing, it requires approval from the University Chemical Radiation Technical Committee. This involved an extensive risk assessment, safe operating procedure, and Australian standard compliance. Given ammonia's toxicity, the main concern is a leak. This required implementing safety features such as inclusion of a solenoid shut-off valve, exhaust fan operation at all times, gas monitoring, and system isolation. Ammonia is toxic above 25 parts per million over an 8-hour period or 35 parts per million over a 15-minute period. As a gas, it's lighter than air and will raise to the ceiling or into the atmosphere, though in large quantities can form a ground-hugging vapor cloud. Liquid leak behavior is more complex, however. As it flashes to vapor, some ammonia remains a liquid. This is known as two-phase flashing. As such, some leak scenarios were calculated based on varying hole sizes, as you can see here. So first of all, just have the ammonia leak without any control. The second figure shows the ammonia leak rate with the exhaust fan operating, which it begins to taper off, but obviously not enough. Oh, and the black dotted line is the safe exposure limit of 25 parts per million. And finally, ammonia leak rate with exhaust fan operating and applying the solenoid shut off after 10 seconds, which you can see it decays under the safe limit for all hole sizes. Finally, the current state of the project. The proposed cylinder setup along with the pipework came in above our budget, meaning we were not able to procure the ammonia for the project at this time. So from this point onwards, I'll be further developing the system design and honing the baseline petrol results in the hope that the project will continue with another student next year. Okay, so to conclude, future work still required includes improving baseline results, EFI wiring and tuning. I may also improve the ammonia theoretical calculations, though I won't have time to perform proper simulations. So the safety documentation is submitted for approval to committee. And finally, a lot of report writing to submit my final report. Okay, thank you for listening.